Welcome to The Explainer. Today we're diving into what's honestly one of the most critical yet completely underappreciated challenges in analytical chemistry. We're talking about sample introduction in mass spectrometry. Now, the fundamental principles of weighing molecules have been around since the 1890s, right? But before we can do any of the cool stuff like sequence proteins or identify disease markers, we hit a massive physical roadblock. How do we actually take a physical sample from our everyday world and get it inside the machine? Let's figure out how we get past the bouncer.
Think about the physics of this for a second. We know that to manipulate ions without them just constantly crashing into atmospheric molecules, the inside of the mass analyzer has to be a total vacuum. So if you try to just, open a door and shove a solid rock, a chunk of tissue, or a beaker of liquid straight in, atmospheric air is going to rush in, the pressure spikes, and you literally catastrophically ruin a highly sensitive, incredibly expensive machine. It's a non-starter.
And getting this right is a huge deal, because mastering sample introduction is what lets us do some pretty amazing things in the real world. We're talking airport security screening for trace explosives. In biotech, it's how we sequence proteins and oligonucleotides. The pharma industry, they rely on it for literally every phase of drug development. We use it in clinics to spot disease markers in illicit drugs in blood or urine. Environmental scientists use it to monitor air and water quality, and geologists even use it to test petroleum reserves. But here's the catch. Absolutely none of this happens if we can't safely get the sample inside the instrument first.
Okay, taking a look at this diagram of an electron ionization chamber, you'll see the usual suspects: the electron beam, the repeller plate, the accelerating plates. But I want you to draw your attention over to the far left edge. See that little tube labeled From Sample System? That right there is the mysterious doorway we're exploring today. Before those high-energy electrons can even think about bombarding a sample to create ions, a steady stream of molecules has to seamlessly cross that threshold and enter the chamber. I actually like to think of the mass spectrometer as an incredibly exclusive VIP club. Out here in our normal lab environment, we're all hanging out comfortably at 1 atmosphere of pressure. But inside the mass spectrometer's ionization source, it's operating at just a tiny fraction of a millimeter of mercury, and it drops even lower than that, down to mere micrometers once you get into the mass analyzer. Getting past the bouncer at the front door means finding a way to cross that massive pressure drop safely.
So Section 1, Gases and the Molecular Leak. Let's kick things off with our easiest guests. These are the samples that are already in a gaseous state and just need the simplest entrance.
Since gases are already vaporized, we don't have to heat them up or coax them into the gas phase. But we still can't just throw a valve wide open. First, the sample gets introduced into a larger reservoir that's partially evacuated. From there, the vapor is naturally drawn toward the even lower pressure of the ionization chamber. Now, to stop a sudden rush of gas that would totally overwhelm the vacuum pumps, the molecules are squeezed through a tiny pinhole. It's a really brilliant mechanical bottleneck, the molecular leak. It ensures a steady, totally manageable stream of molecules safely enters that high vacuum. And, we can actually use this exact same system for highly volatile liquids or solids, sometimes just popping them into a small oven first to bump up their vapor pressure.
Moving on to Section 2, Solids and the Direct Probe. What happens if your sample isn't a gas and definitely does not want to vaporize easily? Let's talk about our more stubborn guests, non-volatile solid samples.
Some materials have virtually zero vapor pressure at room temperature. We are talking about pressures lower than 10 to the -9th millimeters of mercury. They just won't vaporize on their own, which makes our trusty molecular leak completely useless. For these stubborn molecules, we have to rely on a physical, mechanical intervention, the direct probe.
You can think of the direct probe like a highly specialized VIP pass. The solid sample is placed right onto a thin wire loop or pin at the very tip of the probe. Then, this probe is physically inserted through a series of vacuum locks directly into the ionization chamber. This puts the sample right up close and personal with the ion source. Once it's safely inside the vacuum, the probe can be heated up. This highly localized heat forces the sample to evolve vapor straight into the path of the ionizing electron beam. The absolute key here is temperature control. The operator has to be so careful. You need to heat the sample just enough to vaporize it, but not so much that the molecule thermally decomposes before you can even analyze it.
Now for Section 3, Crowds using GC and LC interfaces. So, we've handled single gases sliding through a leak, and we've got stubborn solids riding in on a probe. But what on earth do we do when a massive, complex crowd of different molecules all show up at the door at the exact same time?
Well, in the real world, whether you're looking at biological or environmental samples, they're almost never pure.
They're massive, messy, complex mixtures. If you let them all rush into the mass spec at once, your resulting spectrum would just be this overlapping, completely unreadable mess. Enter the chromatographer. Hooking a chromatographer up to the mass spectrometer acts like the ultimate bouncer managing a chaotic crowd. It separates the mixture, basically forcing the molecules to form a single file line based on their chemical properties. Because these high-efficiency columns completely separate the compounds, the mass spectrum of each individual component can be determined one by one as they finally exit the column and enter the mass spec.
But of course, there's a catch, and it's a major technical drawback all about speed. The mass spectrometer has to be unbelievably fast. It must completely determine the mass spectrum of one component before the next one exits the chromatography column. If it's even a little too slow, the first substance gets contaminated by the next one riding right on its heels. Because of this, the mass spectrometer has to be capable of obtaining at least one full scan per second over the mass range you care about. And honestly, if you're looking at a narrower range, it needs to scan even faster than that.
Let's look at how the two heavyweights of chromatography actually pull off this direct interface with the vacuum. With gas chromatography mass spectrometry, or GCMS, it's pretty straightforward. The gas stream emerging from the chromatograph is simply admitted through a valve into a tube where it passes right over a molecular leak. Easy enough. But liquid chromatography mass spectrometry, LCMS, is a whole lot trickier because, well, we're dealing with liquid solvents. It requires a very specialized interface that directly couples the HPLC instrument to the mass spec, meticulously stripping away that solvent and transitioning the analyte molecules into the gas phase using really clever techniques like electrospray ionization. And let me tell you, pairing these techniques is incredibly powerful. Because of this setup, that quote-unquote mass spectrometer acts in the role of detector. By hooking these instruments together, you aren't just getting a generic, basic signal that something passed through a column, you are getting the specific, highly detailed mass spectrum of every single component in that complex mixture. Add to that the fact that modern instruments have these built-in computer libraries that can instantly compare those spectral fragmentation patterns with tens of thousands of standard spectra. It literally tells you exactly what just walked through the door.
Wrapping things up with Section 4, the real-world impact. Let's tie all these crazy mechanics back together. I know the engineering behind sample introduction might kind of seem like just a bunch of complex plumbing, but these distinct entrances are exactly what make mass spectrometers so universally adaptable.
Whether it's a volatile gas sliding through a microscopic molecular leak, a non-volatile solid being carefully chauffeured in on a heated direct probe, or a massive chaotic liquid mixture being meticulously sorted by a chromatograph, getting past the bouncer is the first and absolutely most critical step in molecular analysis. These exact techniques are what open the door for everything from discovering groundbreaking pharmaceutical drugs to catching trace explosives at the airport. So here's a thought to leave you with. Now that we've mastered these incredibly ingenious ways of bringing our physical world into the pristine vacuum of the mass spectrometer, what invisible chemical worlds are we going to unlock next? Thanks for joining me on this explainer, and keep questioning the mechanics behind the science.